Hello class, this is Mr. Hart, and in this video I want to talk to you a little bit about acoustic modeling and in general acoustic research, because this is actually something I did in my undergrad experience at BYU in physics. And so I know a lot about acoustic research and some of the methods that they use. And so I just want to give you a glimpse of what you would do if you happen to go into acoustics and some of the things you might experience in acoustics research. So it turns out that a lot of acoustics has to do with modeling sound. And one of the best ways to model sound and get good measurements is in what's called an anechoic chamber. Now you may have heard of these before, but anechoic chambers are actually these rooms that have all these wedges around them, these foam wedges. And then they have these wire floors that you walk on, and underneath the floors there's more wedges, and in the roof there's wedges. And all these things are done so that you can cancel out as much sound as possible. Now, you may not realize it, but when you actually speak and when you are listening to yourself in a room, you're actually hearing a lot of the echo off of the walls in the room. And so if you put these foam wedges, what happens is the sound, instead of echoing off the wall, gets absorbed as it bounces in between these foam wedges and these triangles, and it just disappears. And so it's very unsettling for a lot of people to actually stay in an anechoic chamber, because they aren't used to not hearing their voice come back to them, because you're always outside or in rooms where there's floors and other things that rebound the sound. And so not have that anymore can be quite interesting. And there's actually a video that I'll have you watch as well called "Can Silence Drive You Crazy?" And it'll give you a good feel of what these chambers actually sound like and how they don't reverberate the sound, and how this can cause some interesting effects in people. But the reason why we like anechoic chambers and want anechoic chambers is because it allows us to set up intricate microphone arrays that can pick up sound coming out of certain things. So for example, if you want to model the sounds coming out of a violin, you could take an anechoic chamber and set up these microphones, and you can spin the violin or the microphones, either way, around so that you can get a full profile of what the sound looks like and where the most intense sound is and how this depends on frequency and other things. And so there's anechoic chambers that are designed to take measurements of instruments. The one at BYU actually did a lot of instrument modeling, but you could also do voices and other sounds that you're interested in getting a better profile and understanding them. So a lot of research is done with anechoic chambers to get these acoustic profiles. And the better we understand sound and how it emanates from different things, the better we can account for it in things such as designing auditoriums and theaters and other soundproof areas, or areas where we want more sound, etc. So another room that's actually very useful for modeling sounds is quite the opposite of an anechoic chamber. And it's actually what we call a reverberation chamber. And a reverberation chamber's goal is exactly the opposite. It's to cause as much reverb as possible. So we have very flat walls. You'll often have panels hanging down in certain areas. And your goal is to cause reverberation, but not just to get a lot of it, but to have it occur in certain ways so that it's consistent throughout the entire room. And so what a reverberation chamber aims to do is to measure a consistent sound profile. So for example, a lot of speakers and other systems like that are tested in a reverberation chamber to see how loud the speaker gets and what power rating we can assign to that speaker, and overall how loud we could expect it to be in any given circumstance. And so anything where you're trying to measure the intensity of a certain system, then a reverberation chamber is also very useful. There's other things we can do with it that I won't go into detail with, but it's another chamber that is very useful for acoustic measurement and modeling. Okay. So those are kind of the two big systems or rooms that we'll use for measuring acoustics. But there's all sorts of projects you can do with microphones that you are determining where sound is going. It doesn't necessarily have to fit into one of these rooms. For example, my research was actually dealing with aircraft carriers. So this is actually a really good starting place to look at things that don't fit into a simple chamber, right? The reason this research was of interest, we were funded by the government, the military specifically, because they were wondering how to prevent a problem that they had seen on aircraft carriers. Now, if you think of a takeoff on an aircraft carrier, as big as an aircraft carrier is, it's not the full length of a general airplane runway. And so these things have to get going fast, which means their jets are really loud. And there's not a whole lot of space for the workers on aircraft carriers to go. And so they often go down to these little ledges and other places. And a lot of aircraft carrier workers actually end up experiencing hearing loss over time. And even with protection, headsets, and other things that would prevent sound from coming in, you can still get hearing loss because sometimes the aircraft carrier is so loud from the airplane taking off that the sound waves can actually shake your whole body and shake your internal organs. So even with all that headset protection, it was actually still causing hearing loss because the fluid in their ears was still vibrating from the outside from their skull, which is kind of crazy to think about, but there's really, really loud sounds on aircraft carriers. So what we got to do was a lot of fun. We got to take a F22 Raptor Jet, one of the standard military jets that would often take off from an aircraft carrier, and we actually got to pin it down to a runway, which was really, really cool. We were able to take these different cables and let the jet try to take off basically, but it was stuck to the ground. And while it was stuck to the ground, we were able to take measurements of the sound emanating from this jet plume in the back. So in this picture, you'll notice that there's this huge array of microphones sitting right here. And what we were able to do was to take this microphone array and let it glide down the track or glide down the runway and measure the sound as it was moving. And so the result is that we took this huge sound field by taking all these microphones, moving them in different spots, and we end up getting this sound profile around the back of the jet. Now, obviously, we couldn't get it into every single spot, but you could model the sound at different levels in different areas. And the result is you get something like this. So at specific frequencies, you would get different intensities of sound depending on how tall you are and how far away you were and what location. Now, where my job came in as the computational side, I took these sound measurements, and my goal was to not only get where these sound measurements are, but to propagate them to the entire sound field, because we couldn't put a microphone in every single spot around a jet. That would take forever. And so we had to find a way to extrapolate what the data looked like in between these areas. And so what I was able to do was make a computational model that was able to represent what the sound looked like coming from each individual point. So it's not the exact same as a jet, but it's equivalent. So it's what we call an equivalent source model. And it's able to make a computer make a sound model that was coming from each one of these points such that it recreated the sound field. So this was what we actually measured. This is what we computed with my model in the same spot. And then doing that, we were able to get the entire sound field in this area. Now, unfortunately, because this is a military work, the rest of this information is classified, so I can't actually show you what the rest of the sound field looks like. But we were able to use that information and my computational model and make some recommendations about where people would stand, other things they could do to prevent hearing loss, other preventive measures to decrease the sound, etc., based on these measurements we took. So I just wanted to show you this example because not only is it cool to explain my research to people, but it's also a great example of what acoustics modeling looks like in general. You take real world measurements, you make computational models and other analyses of it, and you can make recommendations and suggestions and experiments based on what you measure. And that's what acousticians do. So I hope you've enjoyed this. I hope you understand a little bit more about what it means to do acoustics and acoustics research. And thank you for watching.